I think it would be good to start today by talking about the central limit theorem in more detail, not proving it, because again, as we're stating it, it's really not a theorem. We are essentially just saying the gist of the central limit theorem. We're using words like large and approximately within a theorem, which technically is not a good thing. You should never use the words large or approximately in a theorem, because what does large mean? It's not precise. What does approximate mean? It's not precise. You can't prove something rigorously without precision. But for the purposes of this class, it's good enough for us. Okay, so we'll call it the gist of the central limit theorem is suppose x1, x2 through xn is a random sample. Okay, when I say random sample, or when you read random sample, it's almost always a good idea to remind yourself, take 5 to 10 seconds to remind yourself what that means. That means this is a list of n independent and identically distributed random variables. Yeah. Independent and identically distributed random variables. IIDRVs. That is all wrapped up in the term random sample of size n. That's implicit by the fact that n is the biggest subscript here. From a population, and realize that since we're thinking of the random sample as not being actual numbers in mathematical statistics, but rather random variables, for us, a population in mathematical statistics is not so much like a group of people, but instead it's a distribution, some other random variable that's got some distribution, a PDF if it's continuous, a PMF if it's discrete. It's specified by some distribution. Does that distribution have to be a parameterized distribution like we're used to? Does it have to be normal or gamma or binomial or whatever? Doesn't technically have to be. It could be some unknown distribution, though for the purposes of this theorem, we do assume it's got a finite mean and a finite variance, with mean mu and variance sigma squared, which of course then also means the standard deviation is sigma. We are assuming these numbers exist, that they are finite numbers. There are distributions, I've mentioned this before, where these numbers don't exist. The mean, for example, doesn't exist. The expected value doesn't exist. Why? Because maybe it's defined by an integral that doesn't converge. Maybe it's an improper integral from 0 to infinity or something, and that improper integral doesn't converge. There are examples of distributions like that. But you would think that maybe they're not readily useful or something. You know, it'd be more useful if there's a finite mean and a finite variance. And you could argue that, but there are perhaps real life situations where an infinite mean, so to speak, is actually more accurate. How would that actually happen? Certainly, if you've got data, any finite set of data is going to have a finite mean, right? Because infinity is not going to be one of the values. What's going to happen if the theoretical mean for the distribution is in fact infinite? It means as you do bigger and bigger sample sizes, the observed value of x bar won't tend towards some specific number. It'll probably tend to get larger and larger as n gets bigger and bigger, with some ups and downs. It would be a jagged graph, but it would tend to get larger and larger as n gets bigger and bigger, evidently like without a horizontal asymptote, you might say. Though that would be hard to just tell for sure whether it's really an infinite mean just from the data. Okay, but it might be an indication that might be a good model. Anyway, coming back to the theorem, we're making the assumptions that these things are finite, that they exist. Then, for large n, there we go. There's There's a vague word within our quote unquote theorem, making this not really a theorem, but just a gist of a theorem. X bar, capital X bar, the sample mean is, here's another vague word, approximately normal with a certain mean and a certain standard variance. I'm going to go ahead and just use symbols here. Approximately n mu sigma squared over little n. That's shorthand for saying X bar is approximately normal with this mean mu and this variance, the original variance divided by n. Really, the only thing significantly new here is the normality. The fact that the mean is mu, we already knew was true from the fact that X bar is unbiased. The mean of X bar is mu. The mean of the mean is the mean. We already knew that before the central limit theorem. That's fairly easy to prove. And in fact, the variance being sigma squared over n is also fairly easy to prove. You prove this one using properties of expected value. You prove this one using properties of variances, assuming that you've got a random sample. So that does assume these variables are independent. That's important for the variance one, at least, that those things are independent. The variance of a sum is the sum of the variances when the variables are independent. The only thing significantly new here is the normality. But it is still just an approximate normality, as opposed to the thing that I called the cornerstone theorem being an exact normality when you're sampling from an exactly normal distribution. And so this central limit theorem, especially in its vague form here, you might sort of say pseudo-justifies, not fully justifies like with a proof, but pseudo-justifies like it's good enough for applications. Though, you know, how large should n be? That depends on how skewed the original population distribution is, perhaps, or maybe how big the variance is. Pseudo-justifies using our formulas for confidence intervals and maybe what we do for hypothesis testing, even when the population is not normal. In fact, the book does talk about this briefly in chapter 8, that these procedures are called robust. That's an official term in statistics. They're robust procedures, meaning that they work still pretty well, even if the hypotheses are not exactly satisfied, as long as the sample size is large enough. But again, that's kind of vague too. Like, what does all that mean? That's what people do with research in statistics. Maybe those kinds of things have already been done, is try to quantify how large is large in various circumstances. How large do you need n to be to get certain levels of goodness in your approximation? That's what people have done some research about in statistics, and maybe still do, probably in more complicated situations. Let's try to understand this theorem now with some simulation. I'm going to do it both with a spreadsheet and with Mathematica, and we'll compare and contrast. Spreadsheet. I could use a normal distribution that I'm sampling from, but it's going to be simpler in a spreadsheet and also instructive to emphasize that the population doesn't have to be normal to use just equals rand. And let's say my distribution is uniform, equals rand simulates sampling from a uniform distribution on the interval from 0 to 1. Let's make it a bigger interval, like 0 to 10 or something. I could do equals 10 times rand to simulate sampling from a uniform distribution on the interval from 0 to 10. So let's simulate over and over again. How many times? How big should my sample size be? Probably bigger than 10. I don't feel like copying and pasting too far. Let's stop at n equals 25, say. So there's a random sample of size 25 from a uniform distribution on the interval from 0 to 10. What's the mean of those numbers? This is like observed values of x1 through x25. You label these little x through little x25. I could do equals average to find their mean, though the spreadsheet is programmed in such a way that when I enter that formula, all the numbers are going to change again. That's okay. It's not a big deal. It's all simulation anyway. It's, you know, if I re-enter it, it's going to be a new simulation. You can copy and paste values into, say, the next column, and it will freeze the values instead of doing an ordinary copy and paste. But I don't really care about that. So there we have 4.98 is the sample mean of this particular random sample of size 25. Close to 5, as it should be. Close to 5. That's an observed value of x bar. You label that with a little x bar. But that's just one observed value of x bar. If I want a feel for what the sampling distribution of x bar looks like, the sampling distribution of capital X bar, I should do these random samples of size 25 over and over and over again, probably hundreds of times, and get hundreds of values of x bar. Okay, I don't have the patience to do it hundreds of times, but let's go at least as far as column Z. That'll be 26 times. Copy and paste these over. Column Z, which on Google Sheets is where it stops unless you add more columns. So now I've got 26 values of x bar, some less than 5, some bigger than 5, some significantly bigger than 5, you might say, on a relative scale, 6.26 there. 3.76 there, but mostly they're pretty close to 5. If I make a histogram of these 26 values of x bar, it should be fairly normal looking by the central limit theorem. Now, maybe it's not enough, 26 of them. In reality, I probably should do hundreds and hundreds of them. Let's see what happens if I highlight those and insert a chart here. Doesn't necessarily pick a histogram, so I have to change it. Histogram. Okay, there's what the histogram looks like in this case. Not super close to looking normal. It's because I only have 26 values of x bar here. Again, if I had hundreds of them, it probably would look more normal. Certainly centered close to 5. What's the standard deviation? We should probably figure that out. So I'm sampling from a normal, from a uniform distribution. The background random variable, call it x, you might say, is uniform on the interval from 0 to 10. Its mean is clearly 5. Its variance, oh, I've forgotten the formula. I think it involved the square root of 12, or was that the standard deviation? Let's quickly look it up. Continuous uniform distribution with that density over the interval from A to B has mean a plus b over 2. That's the midpoint. And yeah, variance b minus a squared over 12. We did derive that 3 or 4 weeks ago. B minus a squared over 12. So that's 10 minus 0 squared over 12. 100 over 12. 50 over 6. 25 over 3. What would that be? 8.3 repeating. And the standard deviation is the square root of that, which you could write as 5 over root 3. And if you want to rationalize the denominator, that's the same as 5 root 3 over 3. Square root of 8.3 repeating, somewhere slightly less than 3. 25 thirds, take the square root, about 2.887. That's the standard deviation of the population. It's not the standard deviation of the sampling distribution of X bar. X bar, when n equals 25, as it was for us, there were 25 rows that we used. N is 25. Then I did 26 columns, 26 values of X bar, but n is 25. I could have done more than 26. I just ran out of letters. N equals 25. The mean of X bar, the mean of the mean is the mean, is the same as mu, the mean of X, still 5. Our histogram that we made was centered on 5. What's the standard what's the variance of X bar? It's the variance of X divided by n. 25 thirds divided by 25. How about that? That simplifies to 1/3. 0.3 repeating. So the standard deviation of X bar is the square root of that. 1/√3, same as √3/3, whatever that turns out to be. Take the square root of 1/3, it's about 0.577. Thinking about either the 68, 95, 99.7 rule or the two standard deviation rule of thumb, practically all the values of X bar should be within 2 times this of 5. 2 sigma X bar is approximately 1.15. 5 plus or minus 1.15. I'm not doing a confidence interval here, by the way, because 5 is not an observed value of X bar, and I'm not using a confidence level or anything like that. I'm just saying what's within 2 standard deviations of the mean. This goes from 3.85 to 6.15, not a confidence interval there. We should expect all these numbers, or almost all of them, to be in that range. Now there was the 6.25 or 6.26, that's slightly outside the range. The 3 something, where was the 3? 3.76 is slightly outside the range. So looks like 24 of the 26 numbers are within the range here. 24 divided by 26, 92%, not too far from 95%, as the 68, 95, 99.7 rule would predict. Thinking about this graph, if you imagine a normal curve being superimposed on this, you would expect the inflection points of the curve to be within 1 standard deviation of the mean, which is about 0.6. So somewhere around 4.4 and 5.6 should be the inflection points. Yeah, I mean, not too, yeah, I mean, it's far from perfect, okay? So we're just trying to get a vague impression of how good it's doing. So there's how you could simulate it in a spreadsheet. Let's look at Mathematica next. So we could use, let's continue doing random samples of size 25. What can we do here? So if I used RandomVariate, uniform distribution on the interval from 0 to 10, I'm not, okay, I think that syntax is not quite right. I think I need that. And after 25 numbers, there I've got 25 observed values from a uniform distribution. I can then take the mean of those and get into value of X bar. I could do this over and over again. I could, in fact, use table and mean, put this code inside the mean, and then do this, say, 1,000 times. So here's a quick way in Mathematica, one quick way of getting 1,000 means from 1,000 random samples of size 25. They should be mostly pretty close to 5. They are, sometimes lower, sometimes higher. I did it 1,000 times. Now the histogram hopefully looks pretty close to normal. Not too bad. Centered at 5. Imagine superimposing a normal curve on this. Are the inflection points at about 4.4 and 5.6? Yeah, it doesn't seem too bad. Right around there for one inflection point. And right around here for the other inflection point. Seems pretty good. Okay. So the point there, both with the spreadsheet and Mathematica, is to illustrate the central limit theorem, its truth. And likewise, at the same time, to try to understand it better. What is it saying? This is an approximation, effectively, to the sampling distribution of capital X bar. And it actually it also doesn't matter whether the background distribution is continuous or discrete. You could still say this gist of a central limit theorem is still, quote unquote, true. Good enough for approximations. Good enough for applied math.